Hey everyone, coming at you right now from Washington, D.C. Appreciate everybody's understanding in me being out. I am doing a couple of videos from here using my niece's easel board, clearly in her little play area, just because I was expecting to be at work to film these videos, and since I'm not, I'm just kind of making use of the resources that I have. So, thanks for the understanding. The one thing that I wanted to go over in class, and since I'm not going to be there to do it on Wednesday, we're going to just take a look at it really briefly right now. In your practice, you've been writing electron configurations for different atoms using the periodic table. And I know I've been having you write a lot of really long electron configurations, especially for elements that are atoms that are further down here on the periodic table, right? Those can be really lengthy electron configurations. Luckily, we have an abbreviated way of writing electron configurations. So that's what I have here for you. And I'm going to walk you through how to do that. But first, I want to look at why we're doing this, why we're able to write these abbreviated electron configurations. So the whole basis of writing these is that we're using noble gases. To understand why we're doing this, we need to understand that when atoms bond, they're only using their valence or their outermost electrons in the reactions. So whenever we're looking at how atoms are reacting with each other, we're looking at their valence electrons, okay? The inner electrons are actually shielded by those outermost electrons, so they're not able to react. So we're only going to look at those valence electrons. Noble gases, which if we look at our periodic table, the noble gases are this very last column, starting with helium and going down. Noble gases have full valence shells. Because they have full valence shells, their outer electrons don't readily react because in bonding, atoms are trying to get a full valence. Noble gases already have that, all right? So it typically means that they're not going to react readily with other atoms in reactions. So knowing that noble gases have a full valence shell and the atoms only use their valence electrons in reactions, this is what's going to allow us to write abbreviated configurations. All right, so I'm gonna pull my easel paper down. How are we going to write abbreviated electron configurations given the why? The first thing you're going to do is you're going to find the element on the periodic table. All right, so I'll walk through these and then we'll do two examples. Find the element on the periodic table, and you're going to find the heaviest noble gas with fewer electrons than that element. All right, heaviest noble gas possible that still has fewer electrons. You're going to write the symbol for that noble gas in brackets, and I have the word brackets in brackets, so you know what the brackets look like. And then you will finish off the electron configuration for the remaining electrons. All right, so let's take a look at what that looks like. All right, so on the periodic table, the very first one we're going to do is cadmium. Right, so if I'm looking at the periodic table, cadmium is right here, Cd. I'm going to need to find the heaviest noble gas with fewer electrons. All right, so that means I'm going to have to look right here. All right, we have xenon here. That has more electrons than cadmium, so that's not going to work. So the heaviest noble gas with fewer electrons is going to be krypton. I don't know if you can see that. Krypton is right there. Okay, so I'm going to write that noble gas symbol in brackets. So I'm going to have krypton, Kr. All right, and then I need to write the electron configuration for the remaining electrons up to cadmium. Okay, so if I'm at krypton here, then the next piece of my electron configuration is right here. Remember, this is the S block. This is going to be 5s. So we'll have 5s2. That takes me to strontium. I'm then in my D block. Now remember, D drops 1. So even though this is 5s, my D block drops down to 4. So this is 4D. 4D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That takes me to cadmium. So it's going to be 5s2, 4d10. 5s2, 4d10. Right? We will do one more together. Let me find where polonium is. All right. So polonium, PO, is the next one that we're going to do together. Polonium is right here on the periodic table. So we need to find the heaviest noble gas with fewer valence electrons. All right, our noble gases are right here. I see that radon is here, but radon has 2 more electrons than polonium. That's not going to work. So we're going to go up here to xenon. Xenon is the heaviest noble gas with fewer valence electrons. So xenon is going to be in my brackets. Xe is my symbol for xenon. Okay? Now, from xenon, we're trying to get to polonium. So we're going to come down here. We have 6s, right? After 6s, we can't jump to the D block because the F block belongs right in here. Even though it's down here, if you look at the number of protons, they actually belong right here. So we're going to have 6s2, right? And that takes us to barium. Then we're going to fall down 2 places, right? So even though this is 6s, we fall down here to 4f, right? So that takes us 4f, and there's 14 here. So 4f14. All right, 4f14, we're back up here. Again, even though this is energy level 6, our D block drops down 1, so this is 5d. 5d, 10, right? 5d10 takes us to mercury. We're at mercury. And then here's our P block. We're back to the normal energy level 6. So this is 6p1, 2, 3, 4. That takes us to polonium. So we're going to have 6p4. All right, so these are a lot easier than writing the entire electron configuration, the full configuration that you guys have been writing. It's just a little shortcut to make it easier for those very large atoms that we might have to do a configuration for.